list recitation session, as I mentioned in the mail to the class. There will be a list recitation session right in this room. We'll get done at 5:45. That starts at 6. And so you can go out, buy something, go whatever, do anything, and come back. And then, 6 to whenever. I think we have the room until 8 or something. But I'm assuming people will start falling before that. So Will Cushing will be doing the list recitation session. As I said, the anatomy of listing that I have, that's also relevant. But you can probably go a little more from the beginning, and then you can also ask him questions because he's here. We will try to record that session too for those of you who actually cannot stay, and then so you can then look at the video. Okay, that's regarding the list presentation. The thinking cap is open, and if you go here. So the people apparently are writing stuff on it. I think about 10 people wrote. And what we are going to do is, I am trying to read them, and so are the two other TAs. Apart from Will Cushing, there is Karthik and Tuanuan. And in fact, we just noticed that finally, after a long time, the blogger folks put a reply to the comments, which is kind of nice because then I can respond to a specific comment. In the past, blog, basically the comments, if I want to respond to one of your comments, I just have to write this and it'll just come in the line. Right now it's indented, so it's almost like both a forum and a comment, a blog kind of a thing. So if something strikes us as particularly interesting or particularly wrong, we will write something there. So this is, as I said, it's a community discussion sort of a thing. The stuff that I read, none of them are egregiously wrong. A couple made me think, so which is good. Essentially, I think Joseph Chunker had a comment about flow theory or something from psychology. That's interesting. But I do have something for people who actually start doing this when, in fact, it is up, especially given that we still have several people here who haven't yet registered for the blog. That's not a good idea. So make sure that you register for the blog, if you're in the class. And the first guy to have essentially answered something, we said something on the blog, is Kaushik Sarkar. Is he here? Okay, so I have here 2 ice creams. You get one. Since you are the first, you get to choose. There's one with, both of them have the same cookies. There's a cookie place that opened just downstairs. One is freshly baked chocolate and peanut butter cookies with fudge brown in the middle. And one is the same cookies with vanilla in the middle. Which one would you prefer? Fudge brown. Okay, fine. There you go. So you notice that there are sometimes advantages for doing things in time. Okay? And other people get to see you eat. Now, remember I did say that, if you can't be first in a category, make yourself a category where you can be first in. So we need to look for the first 471 student. You are 598 student. The first 471 student who said something, that seems to be John Brannon, if I'm not wrong. So there you go. So you don't get a choice, but you get to eat ice cream if you can. What?
When you scroll down into the replies, you're not ordered directly with the actual time posted.
Oh, really? There are issues now, I guess. John, you almost got it, but yeah, let's see. What happened here? No.
He did post it.
I think he is number 2, as I remember it. Because anytime anything comes, I also get an email. There you go.
I can pass it.
Okay. It looks like a nice place, by the way. It opened, and there are too few things opening and too many things closing on the Mill Avenue. that this looks like a nice place. And the only depressing thing is the guy who is actually doing this, he said he was an electrical engineering graduate student from Carnegie Mellon University. so it seems as if too much of training to put ice cream between cookies, but anyway. Okay, so okay, the other part is that the drop add is over in case you did not notice. And so the only way you can do it is withdraw from the class and lose your tuition dollars. So this is sort of the final tally for the class. There are 46 people. There are 46 seats and there are 46 people in the class. Officially, that's the only people that can be here. That's the number of people who can be here. And just so you have an idea, there are 28, 471 students, of which this percentage is actually wrong. Forgot to change that. And then of which one is a sophomore, actually an exchange student, 3 juniors, and 24 seniors. Okay, and then 598 section, there are 18 of them, 1 PhD, 13 masters, and 4 MCS, which is a different kind of masters. Okay, so those are the that's sort of the makeup of the class. As I said, 471 and 598 will be seen as different classes when giving the grades, but otherwise it's the same. So you have the same exams, same assignments, but eventually your grade will be in comparison to the section that you are in. Okay. Of course, it's also could be a time for buyer's remorse as to what did you get yourself into. I do want to point out that irrespective of how much work is involved, this is actually a comment that a student, it's an unedited comment that a student made last time around in the class evaluations. And I believe that that's in fact true, not this part and this part, but definitely this, that the AI, this course essentially really is at the top of your food chain. So a lot of things that you learned in freshman, sophomore, junior years, maybe even senior year, would be useful. Would you actually wind up using it in basically analyzing what we wind up doing? AI is not a philosophical course; it's a computational course, and we use computer science. And you will, wind up having it's sort of a capstone in some sense, for the whole of computer science. So I think, yeah, you'll enjoy it. So hopefully, not too much of a remorse for that. Okay, are there any questions before we go forward? Okay, so what I'm going to do today is to start from here and start talking about what I call atomic agents, a particular kind of intelligent agents called atomic agents. And let's go back to this picture that we were looking at the end of last class, right? So we were saying that this is sort of a goal-based agent, and I use this picture, this architecture of an intelligent agent, to sort of motivate why we will wind up doing different topics in this course. Okay, so for example, in trying to figure out what the world would be like if I were to do an action, and then using that simulation, mental simulation, to decide what action you should do, what action the agent should do. That whole thing really is search, planning, inference, reasoning. Those are the things that we'll understand there. Okay. The other part is what is the current state, how is the world evolving, and what do my actions do to the world? This is a bunch of knowledge. Okay? And if you have knowledge, you need to represent the knowledge. Okay? And the question, of course, is how do you represent the knowledge? You can do it essentially in atomic way, which is what we'll be talking about starting today, or you can represent the knowledge in logical or propositional or relational way. Okay? And so in understanding the representations, we'll understand logical representations and probabilistic representations. Okay? And finally, of course, in the beginning of the course, most of the course, like 3/4 of the course, we'll assume I know that the programmer knows the model of the world, and they're just inputting that to the agent. Okay? And so they're inputting it in some form, either atomic form or are logical form or probabilistic form. Okay, and the algorithms in the agent will reason with that and decide what is the best action to do next. That's what we'll wind up doing in the beginning of the course. Okay, but as towards the end of the course, we'll start asking, what if I don't write all the model? What if I only write part of it? Can the agent learn more from the experience? Okay, so part of the model is written by the designer and part is learned. And of course, in the best case, in like the extreme case, all of it is learned by the agent. Okay, so that's where learning comes in. So learning basically is learning the models of the world. Okay, you can also learn how to do reasoning better. That's a different kind of learning. But the most obvious case is, learning the knowledge about how the world evolves. What my actions do to the world. That sort of a thing. Okay, so that's where the learning part comes in. So those are the topics that we'll do. So we'll, do this, and this will be interleaved. As I start talking about in the next slide, what we'll wind up doing is we will start talking about atomic agents first, and it turns out, as you'll see in a minute, that for atomic agents there is no representation, because atomic agent means states are indivisible. They're just black boxes. They're like S1, S15, S25. Okay, there's nothing to represent. Okay, so then all you would be focusing on is doing the reasoning over this, doing the search over these representations. That's where we'll first start understanding the A-star search and the various kinds of search strategies. Once we do that, then we go back and say, well, what if we improve our representation so that it's not black box, but it's, let's say, propositional? Okay, then we can come back and say, what would the search look like if I have a propositional representation? That would look like planning, essentially. Okay, and finally, if you have probabilistic reasoning, again, you can come back and say, what does reasoning look like? And then we'll talk about probabilistic reasoning. Okay, that's the approximate idea as to how these topics will be interlinked. We'll start with search, we'll go to logical representations, we'll come back to planning, which is sort of the reasoning over logical representations. And then we'll again go to probabilistic representations, we'll understand how to reason over probabilistic representations. Then we'll talk about learning. Okay, now I did mention these three types of ideas, the three types of representations. So in some sense, apart from, before I came to this picture, I was talking about a variety of agent types. Remember, there was a simple reflex agent, then state-based agent, and then this. Right? That was the third one we looked at last time. So that is one categorization of agents. A different categorization of agents that I'm going to look at, it's a sort of an orthogonal categorization, is how does the agent represent its knowledge? Okay, and there we talk about atomic representations, propositional or factored representations, relational representations, and first-order representations. Okay, now the interesting thing is, of course, there is a slide here with dense amount of rows. We'll come back to this in a minute, but let's actually understand, in some sense, as if anybody in a course, you're doing atomic first, then propositional, then relational, then first-order, it sort of seems to mean that good stuff comes in the end, right? I mean, somehow this must be the dumb way of doing things, and this must be a better way of doing things. Otherwise, why am I not doing these first, right? So what we want to understand in the next slide, essentially, is why are atomic representations are not as good as propositional, and why are propositional not as good as relational? That's what I want you to understand, okay? So that while we are doing atomic search, atomic agents, you still know something can be improved when you figure out how to represent knowledge in a more compact form. Okay, to make that point, and we'll come back to this slide in a minute, but let's go here. This is a very simple vacuum agent, okay, vacuuming agent. So Roomba, think of Roomba, okay? And it's living in a 2-room apartment, okay? And it's in one of the rooms, and there may be dirt in either of the rooms, and the agent's goal, of course, in general, is to presumably remove the dirt. Right? So that's the agent. Okay. So you can start talking about goals for this agent at all. We'll talk about it in a minute. But obviously, what's a goal for an agent? I mean, it's not eating ice cream. It's just, cleaning up the rooms. That's the goal. Okay. So now if you have this kind of a world, so I have 2 rooms and a robot. Clearly, these are the different configurations of the world. This is the as simple a world as you can get. And these are the only configurations. Here is a configuration 1, where the robot is here, and there is dirt here as well as dirt here. In this, the robot is here, there is dirt here, but there is no dirt here. Okay? In this one, the robot is here, no dirt here, and so on. Right? There are no more states here. These are the only states that you have. Okay? So now think of each of these as sort of the snapshots of the robot world, the vacuum agent world. Okay? In the case of atomic representations, essentially what we'll say is there are actually 8 states, S1, etc., up to S8. There are 8 states. Okay? And so now each state is seen as indivisible. It is an atomic state. There is no structure to the state. Okay? And to some extent, when you are talking about doing an action, then in essence what we'll be saying is, if you are in state S1 and you do an action A1, you may go to state S5. Okay? If you are in state S3, you do action A1, you may go to S7. By the way, just since I wrote this, here I wrote, if I am in state S1, I do action A1, I'll go to S5. Is this action deterministic, stochastic, or non-deterministic? Deterministic. Because I told you if I go from this, start from S1, I will go to S5. What if I said if you are in state S1, you do action A1, you will go to S5 or S9?
Non-deterministic.
That's non-deterministic. So you actually, even within this very simple agent, we can talk about deterministic actions, non-deterministic actions. These are transfer functions. Okay, an action is a transfer function which takes state as an argument and gives either a single state or multiple states. And if it's a stochastic one, it would say S1, you do A1, you will get S5 with 0.9 probability, S9 with 0.1 probability. Okay, so that's your atomic agent. Now, any problem, if you don't even understand it at the atomic level, you probably don't understand it. Which is why we will first think about how to do reasoning or search at the atomic level before we take it to the logical and probabilistic levels. Okay? Okay, so this is the atomic idea. Now, the interesting thing is it's very simple. Basically, states are indivisible and actions just take you from state to state. Okay? What's wrong with it? What's wrong with it really is state spaces can be humongous. This is a very small world, and so there are 8 states. Okay? Now, in a more interesting world, there can be way too many states. What that means is now the robot has to sort of have all the information about all these states, at least the numbering of all the states in its head, which is sort of memory consuming. Okay. Second is changing. So for example, I now say I have another Roomba. This is the world, I've bought one more Roomba. So now there are 2 robots hanging around. Suddenly, the number of states doubles. Okay? So it's not S1 to S8, it's now S1 to S16, because I need to talk about the state of the other robot, which can be either room 1 or room 2. And it's not any obvious way. It just doubles, and then you have to write all those states, and you have to basically make sure that these transfer functions are all correct. Okay? So this is, by the way, software engineering. Right? If you just get an extra robot, and you have to change your entire program because you got the extra robot, you would prefer not to get an extra robot. Okay? So you want modularity to your knowledge. Okay? Now, worse yet, suppose apart from caring about just dirtiness of the room, suppose I want to care about the noisiness. And suppose I might be, there may be a person hanging around and they might want to keep certain rooms less noisy, for example. So you want to talk about the noisiness of a room. Let's assume rooms are soundproof. That means if a robot is in one room, the other room, there won't be any noise. But that room, there will be noise. So you have a noise as a property now. Right? So now if you want to talk about noise as a property, now you have noise of room 1, which can be true or false, or high or low, and then noise of room 2, which can be high or low. Okay, all of a sudden now you have quadrupled the state space size. You just quadrupled the state space size. You see what I'm saying? As long as the state space is not going to change, there is nothing wrong. How many of you have been told that you should never write programs with go-tos? If you do languages, programming languages, you've been told that. There's nothing wrong with writing programs with go-tos. If you just write a program once and you'll never again look at it, and nobody ever has to look at it again. It works, why do you care? Ultimately, assembly language has go-tos. The reason they ask you not to use go-tos is because maybe once in a while you may want to look at your program and you have no clue what the heck it's doing because it's going from one place to another place to another place. The control is not obvious to you. And God forbid somebody else has to look at your program. Then they are even more screwed because there is, the control flow is much harder to understand. Okay, so the idea is there's nothing wrong with atomic, but for the fact that it takes too much space and that it's not modular. And that it might have to be changed if there's a minor change to the world. Okay. Now, the next idea we'll look at is a propositional or factored representation. Okay. So what we'll do here essentially is we'll realize that states are not atomic anymore. They're not indivisible. They have structure. Okay. And the structure essentially, you sort of realize this yourself. As I'm telling you, you kind of realize that, it's not that hard to realize that there are actually, some facts that are either true or false. So, for example, you can think of this world in terms of these 3 Boolean valued state variables. You can think of a state variable dirt in left room, which can be the true or false, dirt in right room, which can be the true or false, Roomba in room, which can be left or right. Right? Okay. So there are only three, state variables. Now, of course, the number of states, if you have 3 Boolean state variables, the number of states would be 2 power 3. If you have n Boolean state variables, the number of states will be 2 power n. Another way of looking at is if you have s number of states, then the number of state variables will only be logarithm of s. So you reduced the size of the representation. You see what I'm saying? Now you have a compact representation. Instead of 8, you wrote 3. 8 to 3 is no big deal. But 1024 to 10 is a big deal. 2 power 32 to 32 is a big deal. Right? So you cut down the size of the state space. That you have to, it's not that the states disappeared. They didn't disappear. The transfer function now can be represented much more compactly. Okay? One of the interesting things that the transfer function can do now is instead of saying S1 will take, if you do A1 in S1, you'll go to S5, you can now say, actions can say that if you are in a state where robot, if you are in a state where there is dirt, and then you do an action suck, then no dirt. So you sort of doctor the state. So whatever the state is, if the current state has dirt in that room and you just did a suck action, then it no longer has dirt. Okay? So you can recompute the states now in this algebraic fashion. Okay? So the specification of this kind of actions is now going to be much smaller than the previous specification, where you have to say, what if you do this action in this state? What will happen? In general, in the previous case, to talk about an action A, you need to consider S1 to Sn, S1 to Sn. If you do an action A in S1, then where will I go? So I can think of an action as a matrix. If I do an action in S1, 0, 0, 0, 1, 0, 0, 0. Let's say this is S7. That means if I do action in S1, I will get to S7. Okay? Each action is of the same size. Every action would be of the size S by S. Now, if the S is like 2 power 10, 24, then this is a pretty large matrix. Right? Whereas most actions, if in fact we were able to live in this world and we are here to take this course, it's because we live in a world where actions have localized effects. Imagine as I am talking, I'm kind of doing like this, and suppose, somehow this is connected to all the electrical system and the whole thing just blows up on my face. It's possible in some random world, but thankfully not true in my world. And if it was, at least I wouldn't have been around, because I twiddled enough that I would have probably gone. Okay? So in general, most realistic worlds, actions basically change only certain facets of the states. And that is something that is a part of the world, that's something that you cannot exploit if you have an atomic state representation. Whether the action changes only one variable or all variables, you need the same amount of space to represent the action. Whereas here, the actions that change many things probably will take more space. The actions that change fewer things will take less space to represent. So overall, your representation of the world knowledge will be much more compact. It will be probably logarithmic. Okay? In the worst case, where every action can take you anywhere in the world, then probably they will be both equal. But in most reasonable cases, this guy cannot exploit the fact that you live in a reasonable world. This guy can. That's why we like factored representations more than these. So as we go through this course, we'll be doing atomic agents first, but I'll keep saying, finally we'll get to factored representations. The reason we are kind of slobbering for that is because it has these advantages. Okay? Now, the other advantage, of course, the other disadvantage that we talked about here was when we added a second Roomba, the space doubled. If I add a second Roomba to this representation, what happens to the representation? I just get one more state variable. One more state variable. Of course, if you add 1, in the exponent of 2, then the 2 power n plus 1 is 2 times 2 power n. So it did still double. The space did double, but the representation that I'm using doesn't double. It only increases by 1. Okay, that's the reason we like the factor. Okay, but now, suppose I want to consider noisiness of the rooms. I still need to consider 2 rooms now, because I need to consider noisiness of the room 1, noisiness of room 2. So I increase my representation by 2 variables. Just because I wanted to consider one relation, I had to increase my representation by 2 variables. Okay, now, this thinks that the world is made up of snapshots, which are indivisible. This thinks that there is this idea called epistemological, big word, but basically, what does the representation think the world is made up of? This representation's epistemological commitment is that world is made up of snapshots, indivisible snapshots. This representation's epistemological commitment is that world is made up of facts. True or false? They're facts. What about your world? Is your world either this or something more than that? It's true that there are facts in your world, but really, much more important, your world is full of objects and relations between the objects. Okay, you're all students. I'm a teacher, and there is a relation I am teaching you between me and each of you. Right? Okay, so normally the world is made up of objects and relations between objects. Okay, and the facts then derive from the relation, whether or not a relation holds between a set of objects. That's a fact. Okay, so that is called the relational representations. And the relational representations essentially are great because there may sometimes be many, many, many objects in the world and very few relations between them. And in this case, anytime you add a new relation, in essence, you need to increase the representation by the relation times the number of objects times, if it's a unary relation, that is a relation for one particular, that holds for each object, okay? Then if there are n objects, then there are n new state variables. If in fact there are k robots and are k people, for example, and you want to talk about the relation loves, right? Then you have loves x, y. X can be n number of things, y can be n number of things, where n is the number of objects in the world. So now you suddenly have n square new state variables. That's how this thing starts biting. Okay, whatever this is biting, it's still much better than this because this guy is 2 power that. You understand what I'm saying? Okay, so whereas if you want to take the relations into account from here, you actually talk about relation side. And that's called relational representation. This is sort of a, this slide is a big foreshadowing slide. It sort of explains to you why we will be eventually going to, logical representations and first order representations. But you need to understand this here because otherwise you don't understand why I'm saying first atomic agents and then later on talk about logical agents. Okay? So in the relational representation, the epistemological commitment is world is made up of objects. So in our case, the objects are Roomba, left room, right room, dirt. Okay, and then the relations would be, for example, in robot room, that's a relation. In XY, that is a relation. And similarly, dirty room, that's a relation. In fact, if I have dirty dirty of the room, then I don't need dirt as an object anymore. Dirtiness is just a property. Okay? So again, this is not particularly beyond common sense for you, right? This is how you think about the world. This is how you think about the world you live in. In some sense, this is non-commonsensical. You don't think of the world you live in as snapshots that are indivisible. But yet, many a time using this, you can first start understanding how to represent, how to do search, for example, for these representations first, and then you can extend it to this. And after-wall analogy, for example, is sort of, even though it's not a particularly good analogy. Remember, first you understood, differentiation by this, right? That's how you understood differentiation. How often do you do differentiation like this? Well, of course, you're in computer science. How often do you differentiation at all? Never. Okay, but if you do differentiation, you barely ever use this. But you understand it here, and then you sort of expand it further. So in some sense, thinking of understanding search here, and then you extending it to these representations is what we'll wind up doing. Okay? So now finally the last thing, the good thing about the relational stuff is that noisiness is just a relation. So how many ever rooms are there, you just throw in one more relation, and that's all. You now have, the representation doesn't have to be extended any further. So compactness is what we are talking about. Compactness of representation, which in essence affects compactness of the transfer function, because ultimately the agents are interested in figuring out in their head, if I were to do this action, what will happen? The guy in green shirt, what are you doing with the laptop? Anything related to the class? If not, close it.
Yes, the notes.
Okay. Okay. So, any questions on this? Okay. So, all I said here is written down here again. Okay. In a more probably dense form. So atomic states, you assume that the states are indivisible. There is no internal structure to the states, and the actions now go from states to states directly. Okay, and then you represent them that way. Action takes a state and gives a set of states, or a single state. And then the focus for dealing with atomic states, representation is not a focus because it's very simple. What you really need to do is how to do the search part correctly. And so we'll start with atomic states first, and we'll understand how to do search over state spaces correctly. That's where A star search, for example, comes. Okay? The next is a propositional state, which kind of corresponds to something like propositional logic or base nets, which are both propositional representations. Okay, the states are made up of state variables and that take values. And typically we will look at in this course discrete values. So if the states variables take discrete values, the eventual state space would be finite. If they take, continuous values, then essentially you have a continuous space. Okay, so we will, in this course, although in general you may have a mix of both discrete and continuous state variables, we will mostly focus on discrete state variables. Okay, and then if the focus here is, you of course will still remember all the search you did, but then you sort of retool it to exploit the factored knowledge you have. So you talk about logical reasoning, you do propositional inference and theorem proving in propositional logic, and you essentially that can be then rolled into the search algorithms. And the search becomes more efficient because it now knows the structure of the state. That's something that we'll see. I mean, it's just a statement I'm making right now. But you will realize that if you know and exploit the structure of the state, you can do much better search. As to figure, search basically is being done to decide what action should I do next. And the faster you decide what action to do next, the more successful you would be in life. Right? And then the relational states describe objects in the world and their interrelationships. And then here again, search plus inference. Here you can think of inference in propositional logic or our base nets. And here we'll mostly look at predicate logic. Okay. Relational probabilistic representations exist, but they're kind of beyond the scope of this course. So we'll mostly talk about propositional probabilistic representations. Okay. And then finally, first order is something that I didn't mention in the previous case. One of the interesting things is even if you have discrete state variables, even if you have discrete number of objects, finite number of objects. Okay, so if you go to this slide here, right? If you have a finite number of objects, one of the interesting things is, I said, if I'm talking about loves x, y, and in my knowledge base, in my world, I believe there are the following objects: Rav and Tom and Mary, and so on. Okay. Now clearly, if there are n of these objects, then saying loves x, y in essence is sort of like saying any of these here, any of these here. So n times n, so n square facts here. It's still sort of, and then if you have n square facts, then 2 power these many facts is the number of states. As you go from here to here, you increase the number of facts, and once you get the number of facts, 2 power the number of facts, a number of state variables is the number of states. Right? Am I losing you? I mean, first of all, 2 power n keeps coming in the course, and I normally tend to say that if computer scientists were to have nightmares, it should have 2 power n prominently in it. If you ever dream of a 2 power n, you should wake up sweating. Okay? Because that's the bad thing that can happen to us. But that's just the beginning of the bad thing, unfortunately. Okay? 2 power n is still finite, essentially. Okay? So if there are a finite number of facts, 2 power the finite number of facts is the state space size. It's still not infinite state space size. Okay? All I'm going to say now is, apart from these objects, there happens to be a function called father of. Just a function. And so father of Rao probably exists. There's a name for it. You don't know it, but you can call them you can talk about my father without knowing his name. And you can also talk about my father's father. You can also talk about my father's father's father. You can also talk about my father's 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 father. How many objects can you talk about now? Infinite number. You throw in one function. Your state space has now become infinite. Is this a bug or a feature? Is it a bug or a feature? It depends on which side you are on. If you are in infinite worlds, It's a lovely feature that by just throwing a function, you are able to talk about infinite-sized state spaces without blowing up your head. Because your head is finite, the last I checked. Right? And yet you're able to deal with infinite spaces just by throwing in functions. When you throw in functions, then you go from relational to first-order representations. If you have heard before about predicate logic versus first-order logic, the difference between predicate logic and first-order logic is the moment you have functions, you essentially are talking over infinite state spaces. One function, out the window. Okay? But that's a huge feature in some sense. Because that means now you can deal with much more interesting worlds which are infinitely sized. Okay? So obviously those worlds, this guy has, in fact, neither this nor this nor this have any hope of dealing with them. Because infinity divided by a number is still infinity. Okay? So once you have, so in some sense, you talk about the expressiveness of a representation as how compact does it make the representation. So how big a space are you going to be able to talk about given a small amount of memory for representing your actions. Okay? So that's basically your first order logic. We will talk about first order logic here. There is also should be first order probabilistic logic. We won't talk about it because there are papers being written on it yet. Okay, we know that it should be there because it will be useful to have. It hasn't. People haven't figured out exactly how to do it yet. I mean, there are research level work in it, graduate level work on that, but undergraduate courses it's hard to talk about. In fact, as I said, I probably won't even talk about relational probabilistic models here. Okay, so that's a different cut on the course. There are 3 different kinds of agents, but mostly, we are not interested in the other agents. We are only interested in this one. This is a good agent. On the other hand, you can also split the agents in terms of the representational commitments they make, and we are interested in all of them. First we will look at these, then look at these, then look at these, then look at these. Okay? Questions? A lot has been said here. Hopefully this will sort of stay in the back. I mean, I almost entertained the idea of putting a big star on this and this, because these 2 slides, you can come back to it every once in a while and see what more can you get out of it now that you went through half of the course. Okay? If you got all of it now itself, great, good for you. Okay? But, there's a lot of consequences of what we just said there. Okay? So, having said all that, I'm going to say that I'm going to focus mostly on the state space, on the explicit state space, or the atomic agents. I know they have problems. I'm committing to get here and eventually here. But for now, I'll do this, and when I do this, as I said last time, get to talk about search. So that's why atomic agents are also called search-based agents. All agents do search, but atomic agents only do search. Nothing else. Okay? So atomic or problem-solving agents, here is a program for writing one of those for yourself. Okay? All it is basically, it's a pseudocode. So you first have to formulate a goal for your... so now one interesting question is, as I said, for atomic agents, an action really, and an action has to be written as an S by S matrix. Each action is an S by S matrix. Okay, now since you're writing a program, of course you can write them as these big matrices, which would be sort of declarative representation. That means the entire matrix is given as an input to the program. The other option is you can write a function. It's a computer program, right? So I will say, give me, I have a child generator function for this particular problem. It takes a state, outputs operator, state, operator, state, operator, state, tuples out. So what it's essentially saying is, in this problem, if you were to start from S, you can reach this state doing this operator, this state doing this operator. Operate is another name for action. and this state doing this action. Now, all the knowledge is right now in this program. Okay? Unfortunately, the search algorithm doesn't analyze programs. So as far as the search algorithm is concerned, it's a black box. It calls, it basically generates the goal, generates the problem, which basically says, go from the current state to the goal state, and then searches. And the search part we'll see in a minute, but search part involves essentially calling this child generator function repeatedly. Okay, so I know I'm in this state. I ask myself, what children can I have if I'm in this state? So I call this function. That will tell me these are the children you get to have. If you do O1, you get S1, O2, S2, O3, S3. Now I can go to one of these states and say, what children can I get to have? Okay, and then I again get new states below that. And then basically I have a goal, right? So I have a goal test function, one more opaque piece of code that you wrote. Okay, and every once in a while, you basically, every time you're about to expand a node, expand basically means if I'm here, where else can I go from here by just doing one action? Before doing this, you ask, am I done? Is this where I wanted to get to? And the goal test function says yes or no. Okay, and if it says yes, you say, very nice, I'm done. And then you just basically give the path and take the first operator in that path and say that's the action I'm supposed to do. So the picture that I just drew in A is this. So you started from some S0 and you called child generator function under S0. It said if you do O1 you'll get S1, O2 you'll get S2, O3 you'll get S3. And then you came, let's say you picked this for some reason and asked, am I done? And I tell you, no, you're not done. Your goal test function says you're not done. Then you say, what are my children? Then I'll say O11. If you do O11, you'll get S11. O12, you'll get S12. Now, for some reason, I pick this. And then I say, am I done? And you're lucky today. I'll say, yes, you're done. Then this is goal. At this point, I just need to remember how did I get here. So I need to, in my program, have data structures which tell me that I got here from here, I got here from here. And then reverse the path and do the first action in the path. And if in fact your world is static and there is nobody else, then you can do first action, second action, and then declare success. Do you see what I'm saying? If on the other hand, if your world is not actually static, it is dynamic, but you approximated it to be static, then you do the first action and then check again to see whether you are in this state or not. If you're not in this state, then you restart the search again and do the first action from that path. That's the basic atomic agent. That's the basic atomic agent. Okay? So in some sense, in this picture, the interesting part is to give the problem, I needed to have given you a child generator function, which is an opaque piece of code, okay, and a goal test function, another opaque piece of code. When I do this, I have given you knowledge, essentially, procedurally represented knowledge. Okay, and since the search algorithm doesn't quite know how you generated them, and it basically only gets state numbers, it doesn't know any structure of the state. So even if the goal comes and bites it, it still won't know. It has to ask the goal test, do you think I'm in the goal? And the goal test function will say, yes, you're in the goal. Or no, you're not. So if that's all you're doing, interestingly, you would think there's very little left here to do. Right? Basically, you just draw a tree and then keep picking nodes to expand. The interesting part is all of search theory is how do you, so think about this. You started with a queue that just had S0. And you removed S0 and you called child generator function, you got S1, S2, S3. So in your search queue, you now have S1, S2, S3. First question, which order did you put them in? I didn't tell you how I put them in. I just said, I somehow picked S1 next. So one issue is, how do you enqueue them so that when you dequeue, depending on the way you enqueue the nodes into the search queue, the algorithm's behavior will change completely. So for example, in this case, I picked S1 then, and I expanded, and I got S11, S12. So now S1 is gone, and there are S11, S12. Where exactly are S11, S12 be, S11 and S12 going to be placed with respect to S2 and S3? Are they going to be above? And that means they get picked before S2 and S3? In which case, those guys will say, like the other guy said, we are here first. You should deal with us first. Okay, so or you put them at the bottom, in which case you deal with them in the order they got onto the queue. So one is last in, first out. If you put the new guys at the top of the queue, that's last in, first out. The other is first in, first out. The new guys go to the back of the queue. Okay? Just looks like a small change in the search algorithm. But you guys know, right? You done 310, and you know that these correspond to completely different search algorithms. Who can tell me what LIFO corresponds to? We will talk about it anyway. It's okay if you don't remember, but somebody might remember. If you put them in last in, first out, depth first. Depth first. If you do first in, first out, you'll get breadth first. Neither last in, first out, nor first in, first out is actually taking into account the promise of the state. Suppose I give you yet another function called heuristic function, which you can apply to your state, and it'll give you a number saying how promising this node is. And then you use that to put it in the queue. So it'll be a prioritized queue. If you do that, essentially you're getting A star search and its variants. Okay, there is depth first, there's breadth first, and if you also throw in the heuristic function, depth and breadth first search are called blind search algorithms. In the sense, they only care about how did you get to this state, not how far are you from the goal. To be able to figure out how far are you from the goal, you need one more function, one more opaque piece of code, which is heuristic function. If I were to supply that, you would then call these informed search algorithms because they have heuristics. And because they have heuristics, they can now put these in the queue in a prioritized fashion. And the prioritized fashion obviously should work better than blind search in general. And when we get to prioritized queues, we'll talk about A star search. And for particular kinds of heuristic functions, they have these beautiful properties that, in fact, A star search can be humongously better than depth first and breadth first search. So that's the promise of the next couple of classes. But before we get there, what I want to do, so this is essentially, I'm assuming that in the atomic agency, I'm basically going to start talking about a single initial state, starting from a single initial state and go to a goal-bearing state. That means a state which has the goal property. That's what the search I was talking about here is. We'll get to it soon enough. But I want you to understand, because it will be again a while before we get back to that, that if you have a single initial state, that means you know where you are. If you know where you are, what kind of an environment are you in?
Accessible.
Fully observable, accessible environment. What if you don't know where you are? That's possible, right? There is less sensing. Okay? I mean, if you have no sensing whatsoever. So get back to, let's say, our vacuum world, which is the same picture that you saw before, with a lot more text. And so in this case, the actions are shut off, forward, suck, etc. And then you can then write these actions into your child generator function. And so the search algorithm doesn't know any structure of the state, but the child generator function basically uses that to decide what new states are generated. Okay? So that's sort of a procedural representation. And the goal, of course, typically the normal goal is that both rooms should be clean, then you stop. But a real robot never is done. Roomba robot never gets done. It just keeps going around and around and around until I guess it dies. Okay? And life never ends until you die. And basically, you get piecemeal rewards. Like, for doing blog, you get ice cream. For not doing well in the homework, you get bad marks. At the end of the semester, you get some grade. That's still not the end of the course. I mean, that's the end of the course at least, but not end of your life, right? So you get rewards on the way based on your behavior. Okay, so in the vacuum agent case, you can maybe give plus 100 for each piece of dirt that you clean up, minus 100, minus 1 for each action that you do, basically because the more time you take, without cleaning anything, the more time you're wasting. So then you want to stop that kind of a behavior. So minus 1 for just random actions. Any action, will have minus 1. And if by that action you get to a state where you get to suck dirt, then you get plus 100. Right? That's how life is. Going through school, is that fun? At least one person should say yes. Right? I'm assuming that most of you think it's like a necessary evil. And then there is like a rainbow at the end of the school and that you want to get to. I would like to tell you there isn't any, and this is as much fun as you will get. But on the other hand, continue in your delusion, and then the point is that you're somehow going through the courses which are all negative, 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 because you want to get your pay dirt, Google job or something. Right, that plus 100 that you're going to get in the end. And then you'll get fired or something, and so that'll be a minus 1,000 or something. But it never ends, right? So the point is, actions generally can have cost, negative cost, and then some states you might get positive rewards. Okay, so this will basically get you into a more interesting kind of an agent. We won't talk about it for now. We will still talk about mostly simple goal agents. Okay, now even with a simple goal agent, that means all this agent does is it just needs to start from wherever it is and make sure that both the rooms are clean and then stop. And it's done. It gets a grade and it gets to go home to the vacuum world. Okay. So the question then is, assuming still atomic representations, okay, we already understand how single state, you can start from single state. Now the interesting thing is that you may also be starting from multiple states. Let me actually, if you are starting from single state, let's go here. If you are starting from single state, then essentially you are searching in this state space graph. Every state in this vacuum world is one of these boxes. Okay? If I tell you which state you start in, you start from this state. And I always told you that the goal is both rooms are clean. That means really either this or this is a goal state. Either of them are a goal state. Right? Either of them is a goal state. Okay, so in this problem, basically finding the best action to do is searching on this graph for a path from where you are to one of the goal states. You did graph search in 310, right? 310 data structures, you did graph search. That's what we are doing here. The big difference is our graphs are ginormous. They typically don't fit in main memory. They don't even fit in secondary memory. They are implicitly specified. The graph is known to this guy, the child generator function. And it will give you the piece of the graph as you ask. When I started from S0, I didn't know where the heck I am. I called the child generator function, and it said, oh, by the way, you have S1, S2, S3 below you. Then when I called child generator function here, it said S11, S12. So it's sort of slowly showing me the part of the graph that I'm asking for. This way, the graph can be infinite, and you still can do it. You can still do the problem. Okay, one of the most interesting things is, what if the graph has infinitely long paths, but the solutions are at finite depth from where you are? As a good computer scientist, you still should be able to write algorithms that will give you the solutions. You can't just say, the world is so big, so I'm not going to do anything. That makes no sense. Okay, so that's the big difference between the single state search that we are talking about here and the graph search that you looked at in 310. These are implicit graphs, and these are potentially infinitely sized. Okay, that's the big difference. Okay, but you understand this. This is the state space graph here. Now, suppose the robot doesn't know which state it is in, which is very reasonable. Now, Roomba won't be told beforehand every day that, by the way, room 1 has dirt, room 7 has no dirt, room 35 has dirt again. And then you are, and then just basically do your thing. That if you have to tell that much, you may as well just go to those rooms and clean it yourself. Right? So you typically don't tell Roomba this information. And the Roomba doesn't have, you're paying $200. And in like Costco, you probably get it for $100, right? And so it doesn't really have like overhead mounted cameras over all the rooms, and it knows exactly where the dirt is. So for Roomba the robot, your house is inaccessible. It's partially accessible or inaccessible. Okay? So fully inaccessible means it doesn't even know what dirt is. Right? Right? And partially accessible means it knows whether or not there is dirt in the room it is in, but it doesn't know anything more. Okay, my question is, can we do atomic agents for that scenario? Just because atomic agents have, atomic representation doesn't mean that the world becomes easier for them. You still have to deal with this. So think about what happens if, in fact, Roomba the robot now does not know at all where it is. What does it mean for not knowing where it is? If the Roomba robot doesn't know where it is, what is the set of states it can possibly be in? One of these 8 states. One of the 8 states. You see that? Okay? So, if you don't have sensing, you don't know which state you are in, you typically know only the set of states you are in. If you have 0 sensing, you assume that you are in any one of the full set of states. If you have partial sensing, you know that it's somewhere between 1 and the total number of states. Lack of sensing means you don't know where you are. You could be in here or here or here. Okay, that's where localization comes. You don't know exactly which room you are in, but then you might be able to sort of still live by, maybe sensing or, or maybe sometimes not even sensing. So in fact, let's get to this. So if you do not have, this is a beautiful slide because it has all sorts of stuff written on it, and some of which will make sense to you now right away, but some again, hopefully you'll come back to. Okay, if you do not have any kind of sensor, the Roomba the robot doesn't have any kind of sensor, then your initial state is this. Your initial state now is a set of states. Isn't that beautiful? So if there are n state variables, there are 2 power n states. And if you lose eyesight, your state space size is 2 power n. When you start thinking, man, my friend who has a couple of sensing missing is having more fun than me, think about this. Essentially, they are searching in a much, much larger space. That's quantifying loss of sensing. So you see what I'm saying? So instead of searching in a 2 power n graph, you're now searching in a 2 power n graph. Or instead of searching in a s-sized graph, you're now searching in a 2 power s-sized graph. That's a huge, big increase. Okay, so now it turns out that this particular problem is easy enough that I can draw the entire state space graph on a single slide. And this is it. And the beauty of this is, if I'm here and I have no eyes, the Roomba the robot has no eyes, can I still succeed?
Yeah.
Yes. Blind people succeed. Not everything can they do, but they can do a whole bunch of things. It's not that they can't do anything either. Okay, so if you are searching without knowing where you are, in essence, this is what's called conformant planning. Okay, so you are non-sense planning, no sense planning. Okay, so without looking, you can still do work. Okay, and in this particular case, essentially, one of the things that happens is if you are in any of these states and you go left, if you do the left action, interestingly, you're now in only 4 states. Do you notice this? The reason actually this works is because actions can reduce state uncertainty. This is state uncertainty. You don't know where you are. But you just hang around and keep bitching and moaning and whining, you'll still not know where you are. But if you keep walking, you'll figure out where you are. That's exactly what this is saying. You will not always figure out what you are, but in some cases, by doing actions, you can reduce uncertainty. Okay? That's a good time to talk about the second joke that BBC had. You remember we talked about the jokes that BBC had as to which is the best joke in the world, and I told you the Sherlock Holmes and Watson joke, but that is the one that was voted the best joke by the Britishers. Now, obviously, there also was a same poll in US, and we are like a much more macho kind of country. We don't particularly care about people with top hats going on, trekking and all that stuff. So there's a different joke that actually won the competition in the US, and that goes like this. So this man and his friend in Texas, perhaps, went on animal hunting. Okay, and then something happened, and then one of these guys, basically his friend, keeled over. So this guy calls the 911. Says, "Oh man, I think my friend is dead. What do I do?" So the telephone operator says, "Calm down, sir. First we need to figure out whether your friend is dead." And then he says, "Okay." And then there is some silence, and he goes away from the phone. There's a big bang, and he comes back and says, "Yes, he is dead." Okay? He reduced state uncertainty. Right? By just doing action, he reduced state uncertainty. This was considered the best joke by the gun-wielding Americans. But anyway, but the point I'm trying to say is the reason these things work is because actions can reduce as well as increase state uncertainty. Okay? So if you don't have eyes, you may still succeed for certain classes of goals. Okay? So sensing, basically actions can reduce state uncertainty, and the state of belief state, these states are called belief states. Instead of normal world states, these are belief states. This basically says, I believe I'm in one of these states. So think of them as belief states. Okay, I believe I'm in one of these. After this, I believe I will be in one of these. After this, I believe I will be in one of these too. After this, I believe I will be in one of these too. After this, I believe I will be in this state. So this path will get me where I want to go. Okay? You don't need Texans to tell you this. You wake up in an unfamiliar place. I don't know how many of you wake up in unfamiliar places, but in the middle of the night, and you don't quite know where the bathroom is, and you can't put on the light because you might be waking up other people that you are hanging around with. So do you give up? How do you get to the bathroom? Most people will basically find the wall and then follow the wall until they find the bathroom. I mean, of course, assuming that it's really pitch dark. Okay? What did you do? You kept doing actions until you reduced your state uncertainty. Okay? Which is why there's this joke that Helen Keller used to tell about herself, that when her mother got mad at her, Helen Keller is, this blind person, remember, that her mother got mad at her, she would put her in a cylindrical shaped room. Because as you go around, you have no clue. By just tactile sensing, you don't necessarily know where you are. Okay? So, again, in this case, even without sensing, you are able to do search, but in a much larger space, and a search in a multi-agent state, multi-state search, the algorithm you write, the algorithm that you write for this, interestingly enough, will work for these two. Right? Because all that algorithm is calling is child generator function, goal test function. You just change those two functions and your search algorithm will work as if nothing changed. Beautiful. It takes much longer time. You'll get probably bored to death as it's checking along, but it will get done. Now this would make it look as if in both this and this case, when you do find a solution, the solution is a single path. It's just a straight line path. Remember that. And then you just do the first action in that straight line path. Okay. And then I also mentioned here that actions reduce uncertainty. Notice that actions can sometimes reduce state uncertainty. They don't always have to. Sometimes they can increase uncertainty. Okay. Great uncertainty reduction is basically if I don't know what is all on the table and I need to clean the table, I can keep looking and removing each one of them, or I can just basically pull the entire tablecloth out. Then everything will be gone. And if you don't know if Iraq has or does not have weapons of mass destruction, but at the end of the war, you know. Right? Before, you don't know necessarily. By the end of the war, you know. Okay, that's another way. Okay, so you can do many, many problems apparently without sensing. The question is, do you ever need sensing at all? If we just have a big computer, do we need eyes? If you have a big computer, you can do search on a bigger graph, right? So when exactly do you need sensing? I mean, I just showed you a case where essentially you are able to solve the problem anyway. Yes?
No, but this assuming there's a finite number of states.
Yeah, but even if there is finite number of states. So would you then say that I don't need eyes if I am in a world of finite number of states? No. So think about this case. Tell me a goal that the robot could not have probably satisfied. I mean, think about this. It's not all that obvious, but think about whether there are goals in this scenario that cannot be satisfied if you don't have any sensing at all. Okay, and I'll give you one which is much more compelling and it's easier to think of, which is, so if we can solve problems without sensor, then why have sensing at all? The reason is, in fact, you can't solve all the problems. There are problems that you can't solve. An example is medication. There are many, many toxic medicines which will make you slightly better than where you are if you have that disease. If you don't have that disease and you take that medicine, you get worse than where you are. It's like, you don't willy-nilly go to the hospital and say, give me some chemotherapy. I heard it's good medication, give me some. Right? It's not good for you necessarily. It's actually highly toxic. But, for the people who are about to, basically in the advanced stages of cancer, the cost benefit works out in their favor. So here is an example which I talk about, which is, it's like a canonical example that makes you remember why sensing is needed. Okay, so here is a situation where I'm trying, I made up a scenario where somebody goes into like a nuclear plant and he may or may not have been radiated. If they got radiated, they'll get this disease. When they got radiated, the question is, if they get radiated, they may or may not have gotten this disease. We don't quite know whether they have this disease or not. So there is this medicine that will cure them if they have this disease. But the same medicine will kill them if they don't have the disease. It's a very reasonable scenario. Now, conformant planning obviously is not going to do it for you, because it will kill a bunch of people and also save a bunch of people. And apparently there is this Hippocratic oath which says that first do no harm. First don't kill patients. Before actually stopping them from dying, at least stop killing them yourself. Right? Now the question is, how do you do that? In this case, essentially, you need testing. So basically what we would do is we test whether or not they have this disease. So the normal thing that might do is, for example, so here you do, after the radiation, in the beginning, this agent knew it was alive and it was not, it had no disease, okay, and everything was good and fine. And then they got radiated, so they may either have disease and alive or don't have disease and are alive. They don't know which state they are in. And they came to your office, you don't know which state they are in. You know that they're alive in both states, that's why they walked to your office, okay, but they either have disease or don't have disease. So there is state uncertainty. Okay? So then you give a test to them. And the test basically involves taking this foul-smelling liquid, which then, if you have the disease, your tongue will turn red. If not, your tongue won't turn red. Okay? So then after this, basically this test has this interesting finding that if you are in the disease state, you will have red tongue. If you are in the non-disease state, you won't have red tongue. The interesting thing is, like the Schrodinger's cat, the doctor still doesn't know whether the patient has disease or not. But the medicine knows, the test knows. And the test has made sure that the state you are in, either you are in this state or in this state. Now the interesting thing is R is perfectly correlated with D and not R is perfectly correlated with not D. So now all the doctor has to do is to get their costly glasses, eyeglasses, put them on and check. Put your tongue out, I'll see whether it's red or not. And if it's red, if the tongue is red, then they are in the DAR state. If the tongue is not red, then they are not D, A, not R state. So if you are in this side, I won't give you medicine. If you are in this side, I'll give you medicine. This is how real world works. Right? This is what you do when you do sensing. Right? Now the beautiful thing is up until here, you are in belief states. It's a belief state of singleton, one state. Here it's a belief state of two states. Here it's still a belief state of two states. Right? But then after you do sensing, the belief state got split into two states. So the sensing resolves the uncertainty. Just as doing actions resolves the uncertainty, but it also changes the world. Sensing doesn't change the world. It just resolves the uncertainty. It tells you you are in this or in this state, for sure. Now, at the time of planning, at the time of execution, you know you'll only actually follow one of these paths. At the time of planning, when you're thinking ahead, you don't know whether, when you look at the patient's tongue, whether they will have red tongue or not red tongue. You don't know. So you need to make contingency plans for both this and this. So your original solution now is no longer a straight line solution. It is a tree. Whenever there is a sensing, the solution splits into branches. And every branch needs to be driven down to the goal. You see that? Okay? So if you have multiple states and you have sensing, then unfortunately the A-star search algorithm you wrote is no longer going to be useful. Because that looks for paths in the graphs. Now you need subgraphs in graphs. In general, a conditional plan is a subgraph in the graph. So that's a much harder problem. I mean, much harder algorithmically problem. The other one is just much harder in the size of the problem. You didn't have to change a line of your code. This one you actually have to write new code to do this. That's basically contingency planners. Okay? So we basically talked about these. We talked about the single state, and we'll come back to this next class. And with respect to single state, remember I said the most important issue is how do you manage the search? How do you manage the search queue? And when we figure that out, which is what we'll be doing for 2 classes at least. First we'll do depth first, breadth first, and iterative deepening depth first search. Then we'll do A-star search. Okay? And by then, we have understood how to do search whenever the solution is a single line. That means just a single path in a graph. And so that applies here as well as here. Okay? For now, we won't work on this. We'll get back to this later maybe, but we won't work on this later. Okay? So we will end here. Okay? So you can take a break, and those of you who want to stay back for the list.